This is going to be a lesson on a triangle's degrees of freedom. Now in this lesson, we'd like to answer a particular question. What is the minimum amount of information you'd need to fully define a triangle? Now as we can see, there are exactly 6 numbers that are used to describe a triangle. We call these numbers parameters. So I suppose that the real question I'm asking is, can we just pick these 6 parameters to be absolutely anything we like? To help you visualize this, I'm going to go ahead and draw on a slider board. Now I want you to imagine that each of these sliders controls one of the parameters on this triangle over here. These 3 sliders control the size of each angle, and these 3 control the lengths of each side. I've allowed the angles to vary from 0 to 180 degrees, and the sides can go from 0 to 50, say, centimeters. Now I want you to imagine that we found and hired a monkey to control the value of each of these sliders. Now I want you to imagine that we let this monkey grab one of these sliders at random and change the value to anything it likes. Now we're going to place a curtain over the monkey's arms and let it choose all of these values at random. It looks like the monkey's chosen 2 angles that are above 90 degrees for both A and B, but C is less than 90 degrees. Now as for the sides, the monkey's decided that A and C should be really small, but little b should be large. Now the real question is, if we go ahead and draw out this shape, does it make a triangle? Now as you can see, in the monkey's head, we started over here and then walked a distance A. Then we turned an angle B. Then we walked a distance C to get to this point, turned to face this direction, and then walked along to B to get to this point. And then we turned by the angle C that the monkeys instructed us to turn by. As you can see, by letting the monkey randomly choose values, we did not actually end up with a triangle. Now this is a little bit confusing. How do we know when we actually have a proper triangle? In order to show you, I'm going to go ahead and draw on a triangle with some known sides and angles. Now, I'm not interested in solving for the missing angles and sides, but I do want to use this triangle to illustrate a few points to you. Let me go ahead and label all the sides that we have and all the sides that we don't have as well. So you can see that we're missing the angles C and B as well as the side C, but we have all the rest of the information. Now what we're saying is that this picture of this triangle over here contains the exact same information as this list of numbers over here. Now suppose we wanted to solve for these missing pieces of information. How would we actually go about doing that? Now for starters, we could actually use the sine rule to find the value of this capital B over here. Now, if we actually went ahead and did this, we would have the value of capital B. So let me put a yellow ring around it. Now, if you actually looked at this triangle carefully, you'd notice that it actually displays the ambiguous case of the sine rule. This means that in this particular configuration, we can actually have more than one possible value for B, but that's totally okay. Now looking at the original values we had over here, we could also use the cosine rule to find the value of this little c. Now again, since this is an ambiguous triangle, there are also going to be 2 possible values for little c as well. Now finally, since we have the other 2 angles, we can also find the value of capital C using the angle sum of a triangle. Now from this example, you should actually notice a few things. These coordinates over here don't actually uniquely define a single triangle. Instead, there are 2 possible triangles, which I can go ahead and draw. Now, you probably wouldn't have thought of this triangle over here, but maths is tricky like that sometimes. You just feed in a bunch of numbers and the maths just goes ahead and figures out what makes sense given those numbers. Now the next thing to notice is that we started off with 3 pieces of information. And every single time you used an equation, you gained an extra piece of information for free. This immediately tells us what the role of equations are in mathematics. Every single time you give me an equation like this, I actually lose some of my freedom to pick this value to be anything I like. Now even though it looks like you have 6 values that you can choose to be anything you like, anytime you give me an equation, I lose the ability to pick one of them. So that means I'm only able to pick 3 of these for free. And now, given this insight, we can actually go ahead and find the answer to the original question that we posed. Now despite the fact that we have 6 parameters, we also have 3 equations that every single triangle in the world must obey. And now this brings us to the mathematical definition of freedom. Now the number of parameters you can freely set are equal to the number of parameters you started with minus the number of equations you were given. So here we're just saying that the degrees of freedom equals the number of parameters minus the number of equations. And in this particular case we have 6 parameters and 3 equations, so a triangle has exactly 3 degrees of freedom. And now this immediately tells us that our monkey friend over here can set exactly 3 of these sliders to any value that they want. However, there is actually one notable exception. The monkey can set any independent values to anything they like. So suppose the monkey tried to set the values of a, b, and c to some random values. This actually isn't going to work, because this equation over here says that if we know the value of a and b, the value of c gets set for us. But for any other possible combination that the monkey chooses, we can solve for all the missing angles and sides. So mathematically, the degrees of freedom tells us how many parameters we can freely set so that we can solve for all the others. Now there is actually a side effect here. If the monkey only chooses 2 of the values, then the system is underdefined, and we can't actually solve for the missing angles and sides. If on the other hand the monkey tries picking 4 of the values, we'll call this system overdefined. So if we try solving for the missing angles and sides, we'll notice that the order in which we use the equations will change the final answer that we get. And given this information, we've actually completed our discussion on a triangle's degrees of freedom.